activity. You already saw a great talk by Rachel yesterday. Stellar multiplicity, Adam's talking later in the week. Stellar variability, there'll be a few talks. And stellar inclinations, stellar orbital and planetary inclinations. Melaine is going to talk later in the week about that. So we're not going to talk about those today, but I wanted to highlight there are so many ways that a star can influence the planet that forms around it. Okay, so let's start with stellar mass. This is a newish paper, but an oldish result, that as a function of stellar mass, the giant planet occurrence rate turns over. So you don't have a lot of giant planets around small stars. M dwarfs don't have a lot of giant planets, okay? This is an old result, but a newish paper. And this is the opposite result to small planets. So here is a compilation of a few different results from Kepler. So now this is stellar temperature, not stellar mass, but it's effectively the same. Smaller stars are to the left. For small planets, as you go to smaller planets, the occurrence rate just keeps going up, right? Like giant planets turn over, you don't get a lot of giant planets around M stars. Small planets just keep going up. The later to the M dwarfs you go, the more small planets you see. And so this is F, G, and K stars, and these are a few different M star results. And this inset here, shows that for the mid-Ms, even within the mid-Ms, you still see this increase in small planet occurrence rate. So this is continuing on. And this is, again, this is a review talk, but I'm not going to be able to talk about everyone's results, so I'm sorry if I don't talk about your favorite paper. But there are, this result is common in the literature. So giant planets turn over, small planets keep going. What's happening? Seems a little counterintuitive. Part of the reason it seems counterintuitive is because of that very first bullet point I talked about on that first slide. The more material you have available in your protoplanetary disk, the more planets, or the bigger planets you might be able to make. So this is a plot from Heiss-Mulders, 2015. So this is, as a function of the stellar mass, the blue shaded region is an estimate of what the heavy material that's available in the protoplanetary disk. The idea being that the bigger the star you have, the more heavy material you have in the disk. These two plots here show, for the Kepler results, if you use a mass-radius relationship to turn the transiting planet population into a population with mass, and you add up all of the mass that's in the planets we found, how the total mass of planets that we found goes with stellar mass. And you can see they're opposite for small planets, right? The more material you have, the fewer small planets you make. So what's happening? Okay. This is Heiss came back to this a few years later. This is Mulders 2019. This is a paper where he talks about this idea that if you have enough material in the protoplanetary disk, you build a giant planet. And once your planet is large enough, you cut off pebble flow. So pebble accretion is one of the planet formation models. You cut off pebbles migrating inwards to form small planets and have the small planets go in. I'm really towing this line. They told me I have to stay on this line. I need, start here. So the idea is, as you go to larger and larger planets, this is stellar mass again here, you have enough material to create giant planets. This is the creation of a cold giant. So you don't get a lot of cold giants around small stars because they don't have a lot of material. But that means that material is left over to make small planets, right? It hasn't been used up and cut off by the formation of a giant planet or in a bigger disk. So this is the hot super Earth in the paper, and this is the cold giant. So as you go to higher masses, you get very few of these super Earths because the material has gone into the giant planets and the subsequent flow of pebbles has been cut off. So this is a story that hangs together. One prediction of Heiss's models, and as an observer I love a good prediction, is that this should stop at some point. You just can't keep increasing forever, right? Otherwise every brown dwarf would have 100 planets around it. So it must turn over. So Heiss made a prediction that this must turn over. And this is a result from my group that's in prep as the stellar effective temperature here. So again, small planets are on the left. The occurrence rate of sub-Neptunes as a function of time. And you can see there is a turnover. As you get to the smallest stars, you see fewer of these small planets. So there is a turnover as predicted by Heiss. It's not exactly where Heiss predicted. And I will say the little sand in the grain of these works is TRAPPIST-1. TRAPPIST-1 is the smallest star you could possibly be and creditably call yourself a star, and it has 7 rocky planets around it. TRAPPIST-1 is like down here, right? So 2,000 something degrees. So TRAPPIST-1 remains an anomaly, but we do see a turnover. At some point, you do not have enough material to keep making planets. Giant planets or small planets. Okay, let's talk about stellar age. Now, I know James is going to talk about this later in the week, but I just wanted to start us off on this conversation because I think it's a longer conversation than one talk. So this is the planet radius valley that you saw yesterday at least once, with the premise being that the population of small, short-period planets is divided into two populations, a super-Earth population and a sub-Neptune population. So there are a couple of leading theories in the literature. There are many ideas, but these are the two that have gotten the most interest in the literature. One is core-powered mass loss. So this is, as your planet is forming, there's residual heat at the core of the planet, and that residual heat radiates out, and that radiation pressure pushes off the top of the atmosphere of the planet if it's not very strongly held, right? So it just shuffles off the top layer. Oop. Okay. Photoevaporation, this one, photoevaporation is that the radiation from the star takes off the top layer of the planet, right? So in both cases, there's mass loss. You're losing the upper atmosphere, but there's different mechanisms. One is the interior heat, one is the radiation from the star. Now, in both cases, there's a critical mass above which you're heavy enough, you have enough gravity to hold onto your atmosphere, even in the face of core-powered mass loss or photoevaporation. And below which you're too small, you don't have enough gravity, you lose that atmosphere, and you shrink down, and you become a super-Earth. So that's the high-level version of it. Now, these can be difficult to tell apart because they both explain what we see in Kepler very well, but one of the places that they are different is in time, in the time scale that it seems like they occur over. So photoevaporation is expected to happen very early in the planetary system's life. This is age. So while the star is young and active and putting out a lot of energy, especially in high energy radiation, photoevaporation is supposed to happen early. Core-powered mass loss happens the whole time, but seems like it's most efficient around a gigayear, between half a gigayear and 2 gigayears. So they are separated in time. So this is something we can test. So the idea is you start with a lot of sub-Neptunes, and you lose a bunch of them. They become super-Earths. So here is a young sub-Neptunes from TESS. This is a result from Rachel Fernandez from a few years ago. And this is sub-Neptunes from K2 field stars. And you kind of vaguely see that story, right? You see a lot of sub-Neptunes around young stars and not a lot of sub-Neptunes around older stars. Now, if it's photoevaporation, you expect that this population is dropping quickly and is down here when you get to a gigayear. If it's core-powered mass loss, you expect that it's still quite high for a long time, and then over this gigayear starts to drop. So how do we test this? K2 looked at two clusters, Praesepe and Hyades, that have an age of 600 to 800 million years, which is right here in the middle. So we look for hot sub-Neptunes, and we still see lots of hot sub-Neptunes. So whatever the mechanism is that's reducing our population of sub-Neptunes down to super-Earths out here in the field stars hasn't happened yet by 600 to 800 million years. There's still quite a high number of hot sub-Neptunes. So this was a lovely, clean story until this happened. So this was last year, 2 new results came out. Rachel took her original test sample and divided it into 2 age bins. And then Sydney Vark did her own independent study of young test stars at up to 200 million years. And they both found a low rate of hot sub-Neptunes for the very youngest stars. And then Rachel found a higher rate, and I have a high rate for these intermediate stars. And then it drops back down. So our cool story about starting with a lot of sub-Neptunes and then having them erode down to super-Earths is suddenly much more confusing. I would say one of the things that I was originally looking for when I looked at age correlations was migration, right? We don't expect that all of the super-Earths and sub-Neptunes we see in these very short periods actually formed there. We expect that they formed further out and migrate in. So I thought I was looking for timescales of migration. And then when I found this wacky high point, I was like, oh no, what's happened? And then we came up with this whole story about, okay, so it's mass loss, and we get down here. So maybe this is a signature of migration, and this is a signature of mass loss. There's a big maybe. I'm putting a capital M ... ellipses after the maybe. We don't know. But this is a really interesting new result that we need to work out. And the power here is, as you map out planet occurrence as a function of age, you learn something about the physics, right? Like, what are the actual mechanisms happening? And the one thing I want to point out at the end of this result is this question. So if you're married to someone who works on galaxy evolution, which not everybody is, but I am, and you show him this plot, he'll say, well, is it that this system will evolve to become this system, or is it the fact that the Milky Way is very different than it was 5 billion years ago, and any system that formed today would look like this, and any system that formed 5 billion years ago would look like this? And you're like, damn it, Phil. So the galaxy is a very different place than it was 5 to 9 billion years ago. That long ago, it was more clustered, it was more highly irradiated, there were more dynamics. So there's a whole other confounding factor, which is the fact that nothing else stayed the same in that period of time. So we could be telling a nice story about planetary evolution with time, or we could be mapping out the galactic production of planets with time. Either of those is pretty cool, but right now I think we don't have a good answer to that. Okay, stellar age. So now we're up to stellar metallicity. So this is one of the oldest results in exoplanet demographics. This paper here, Gonzalez, 1997, there were 4 planets. And Gonzalez was like, well, look, they're all around high metallicity stars. That's interesting. So if you're grad students, if you're ever worried about your sample size, there were 4 planets in this first paper being like, seems like there might be a metallicity correlation here. And then, a decade later, Deborah and Jeff's here, have this canonical relationship showing that as a function of the iron abundance of the star, the occurrence rate of giant planets increases dramatically once you get above solar metallicity, and is quite low below solar metallicity. So then Eric Pettigrew, I think is also here, a decade later again, has this result from Kepler showing that this dependence on the metallicity, so it's still metallicity down here, gets weaker and weaker for smaller planets. So this is the strongest correlation here for Jupiters, and then you get the sub-Neptunes, and then you get the super-Earths. So this is for short period, and this is for intermediate period. So whatever is controlling the relationship between stellar metallicity and planets is weaker and weaker and weaker for smaller and smaller planets. That's interesting, because that tells us something about what that mechanism must be. So one thing I want to point out, do I want to point it out right here? Do I have one more slide? Yes, I want to point it out right here. One thing I want to point out is that these are all using iron, and they're all covering actually quite narrow range of metallicities. It's only minus 0.5 to plus 0.5, which is not a lot in terms of the actual spread of metallicities we see in the galaxy. And in particular, there are planet formation theories that have a prediction that at some low metallicity, you're so low, there's not enough heavy material in the disk, in that protoplanetary disk that we talked about, to make planets, right? At some point, you cut off. You go so low, you can't make planets. So this, I love a prediction. This was a fun prediction to test. So this was work that Kirsten Bowley did with test data. So this is for short period super-Earths. This is the K2 and Kepler data, and showing that same kind of range as before. But she took the 100,000 most metal-poor stars that Tess looked at and looked for super-Earths. Now, if this trend continued, I'm going to try again. If this trend continued, she should have found 68 super-Earths. And she found none. There were no planets in these metal-poor stars. And it was an incredibly statistically significant result that we did not find any low-mass, small planets around low-metallicity stars. So there is a turnover. At some point, this relationship, this super-Earth relationship, just drops off a cliff. At some point, you have too little material to make planets. And exactly where this happened is a super useful input to planet formation theories, because if your planet formation theory predicted a cutoff at -2, then it needs to be tweaked a bit. Okay, so that's just iron, right? Iron's great, but it's only one of them. And we're astronomers, so everything above helium is a metal. So we've got all of these other things to play with. And in particular, this is a really exciting time because of all of these large-scale spectroscopic surveys that are happening. So you have Apogee, you have Galar, you have Lamoste. Hundreds of thousands of stars now have chemical abundance profiles. They don't just have iron, they have all of these interesting elements. And so this top circle here is the superset of the elements that are measured by these 3 surveys. This one here is the superset of elements that are important for rock formation. We want to build rocky planets. What do we need to build a rocky planet? And then this circle here is kind of provocative. This is the elements that are important for life as we know it, right? So if you have a star that doesn't have a lot of these, what does that mean for the planets it can make, and what does that mean for the life that can evolve on those planets? One of the most interesting conversations I had about this was with Natalie Hinkle, where she pointed out that life on Earth is phosphorus limited, right? We use all of the phosphorus we can for life, and if there was more, we could make more. So this is one of these interesting things, like how do we map these relationships to the planets that we find and use that to pinpoint our searches for life? Okay, so just 2 quick results on this. This is a result from more than a decade ago. Yes, I almost thought 2 decades for a second. I was like, no, 2012 was only 13 years ago. It's okay. And so this is metallicity again here, and this is abundance of other elements relative to hydrogen. So this is titanium and this is magnesium. And what this paper showed was that for the planets, the yellow triangles and the blue circles are stars with planets, and the white circles are the stars without planets. For the stars with planets, if they had low iron, they had high alpha abundances. They had high other things. So even if you had low iron, you could make planets if you had other things. And this is just a super tease. This is a brand new thing that I'm working on with Sabina, who's here, using the K2 data and looking at how planet formation changes with the ratio of your iron elements and your alpha abundances. And so the particular thing I want you to take away from this, so this is if you have high iron and high alpha to iron ratio, high iron, low alpha to abundance ratio, low iron, high alpha to iron abundance ratio, and then low and low. So if you have low and low, this is planet radius on the y-axis, you have no giant planets. That's expected, right? That's the same thing we've seen before. But this is really interesting. If you have low iron and high alpha to iron abundance, you have as many giant planets as if you had high iron. So those early results showing this as a function of iron, if you actually control for the alpha to iron ratio, you get as many giant planets if you have a high alpha to iron, which means that the true controlling aspect of making these giant planets isn't iron, it's the total metals that are available. And then if your metals are captured in alpha process elements instead of iron, you still make giant planets. So I think that's really interesting, and Sabina and I are working on that right now. This is great timing. We're now up to the last topic. Okay. Galactic zip code. We live out in the burbs. This is us. This is a top-down view, artist's impression of the Milky Way. But there's a lot of other galaxy. If you actually draw the space that we've been able to search for planets, it's like a little circle around the sun. And then there's one arm towards the center of the galaxy from microlensing, and there's one arm pointing slightly at 90 degrees that's from Kepler. Now look at a cross view. Here's a view to the center of our galaxy. There's the galactic bulge. There's a thin disk of the youngest, most metal-rich stars. There's the thick disk of the older, more metal-poor stars. And then the halo, which is the oldest generation of stars and the most metal-poor. Now, we've already just gone through a bunch of things that affect planets. And these all change as a function of your galactic location. So age increases with your scale height above the galaxy. The older you are, the oldest populations are at the highest scale heights. Metallicity decreases with increasing scale height. The higher you get above the galactic midplane, the fewer heavy elements you have. The dynamical history, these halo stars and thick disk stars have had a longer, more dynamical history than the youngest stars. Their ionization history, the galaxy hasn't just sat there for 13 billion years. It's had starburst eras. It's had ionization history as well. And then I'm just cheeky putting this in at the bottom. Is there a galactic habitable zone, right? Is there a region far enough out from the center where everything looks nice? We're clearly in it, but how big is it? Okay, so let's talk about some results with the galactic zip code. So this is showing as a function of the stellar mass, the planets that you could build if you were a thin disk star, a thick disk star, or a halo. And this is for cool super Earths, this one. So you can see that for the same size star building the same mass planet, you actually have a different radius depending on which population of stars you're in. That's based on equations of state of the material that's available, the temperature, the age, the composition, using an average thin disk star and thick disk star. And this is showing for a 10 Earth mass planet what the radius profile would be I didn't change that, it's supposed to be yellow, for a thin disk star and a thick disk star, showing that thin disk stars are smaller for the same mass than thick disk stars because of this, the metallicity, right? They have a higher metallicity, they have more heavy elements. You plug all that into the equations of state, you get smaller planets. Okay, this is a result of the same Ardebeckian paper from a decade ago. Now, this is like galactic velocity space, and I've never had to think in this before, but it's fun to think in, and it's basically the stars that are within this circle are thin disk stars, and the stars outside that circle are thick disk stars. So in this paper, they came to the conclusion that there are compositional differences that control planets, but not galactic component differences that control planets. They couldn't, they had a pretty small sample, this is all their stars. They couldn't see a galactic difference. This is a result from Kirsten Bowley when she looked at halo stars with TESS and looked at giant planets and found an incredibly low occurrence rate of giant planets in the halo. This can map back to that same relationship we've seen before. The halo stars are very metal poor. We know that metal poor stars don't make a lot of giant planets. So that was consistent. Halo stars don't have a lot of giant planets. And then finally, this is a result from K2 from John Zink from a few years ago. These are the K2 pointings out from us in all different directions. And what John showed was that as a function of the height that you get above the galactic plane, you get a lower and lower and lower occurrence rate for these stars. So the stars that reach the highest above the occurrence of above the midplane have the lowest occurrence of both super-Earths and sub-Neptunes. Now, that could be a metallicity thing, right? We've just talked about how metallicity affects this, but this is the strength of the metallicity relationship that we can see from local stars. So whatever it is stronger than the known metallicity effect, and that's really interesting. Okay, I'm going to finish by talking in terms of galactic zip code about Roman. So Roman's going to launch next year. Very exciting. And one of the things Roman will do is a galactic bulge survey where it will point from us towards the center of the galaxy and stare for different seasons over 5 years. Now, it's going to do a microlensing survey and a transit survey. And what it'll do, I hope, as the demographics working group lead, is that it will map out planets as a function of galactocentric radius. Like, as you get away from the center of the galaxy, what is the population of planets and how does it change? And I think that is really exciting. And this whole idea of planets as a function of galactic location is going to take off in the next 5 years because of Roman. And I will leave up my summary. Physics is really cool. Thank you.
Awesome. Thank you, Jesse. Questions? And we, of course, encourage our early career folks to ask questions.
Hi, Jesse. Great talk. You were talking at some point about the turnover of number of planets per star as a function of stellar effective temperature. Mm-hmm. But then you were like, TRAPPIST is kind of an anomaly. But why would that be? What would make TRAPPIST an anomaly in that case?
Well, it's an anomaly. It's a harder word to say than you might think. Let's get back to it here. It's an anomaly because it's down here. Like, this is a pretty steep turnover. This turnover is pretty steep. And it's down here, and it has 7 planets, 7 rocky planets. I mean, if you truly believed this turnover, and obviously extrapolations are always dangerous, but you would say that below 3,200 Kelvin, you should find no rocky planets. I mean, these are sub-Neptunes, but we see the same thing for super-Earths as well. Nobody's done anything for Earths yet because they're small, and that's what the TRAPPIST ones are. So maybe whatever this is, like the metallicity, just gets weaker and weaker and weaker. Maybe it gets weaker and weaker and weaker for the smaller and smaller and smaller planets. So maybe this relationship doesn't hold down to Earth-sized planets. But if you believed that it held, it would be weird.
Yeah, it's hard to believe that we found TRAPPIST so quickly with so many planets, and that it would be such a huge statistical anomaly without that further explanation, I think.
Yeah, well, it's interesting though, right? Because there's no TRAPPIST-2. And there's a reason there's no TRAPPIST-2. They looked at lots and lots of other stars. So Mirth and Carmenes and TRAPPIST and Speculus, right? Everyone is looking at these tiny stars, and it's TRAPPIST-1. There's no TRAPPIST-2. Stretch.
Yeah, so on that last point, I don't really think this is true. It is true that there is no TRAPPIST-2 system, but if you look with radial velocities, you find planets that could be in systems that are very similar. It's just much, much more difficult to find so many planets in one system. But statistically speaking, there are quite a few other systems probably that are rather like TRAPPIST-1.
Okay.
And
So you're saying like
so
they had 3 planets, but you believe they had 7 planets?
Yeah, so statistically, as there will be longer-term monitoring and we get into the sub-meter per second range, there will be more systems similar to that.
Yeah, I mean, it would be interesting to see if people could publish what they think the distribution of planets around these small stars is with radial velocity. That would be really cool.
We're going to take an online question next.
Oh, yep.
All right, from online, is there any statistics on in situ versus accreted halo stars with planets?
Ooh, is there any evidence about in situ versus
Are
accreted?
there any halo planets, period?
I think there are. I don't think it's 0. I think there's not enough of a sample, I will say. I haven't seen anyone talk about that. Unfortunately, halo stars, you're either finding them, as they're transitioning through the disk at high speed, or they're quite far away. So I don't think we have a big enough sample. Like Kirsten didn't find any. Hers is an upper limit of like 0.18% occurrence rate. So I don't think so. But it's a really interesting idea, right? Like, do you capture these planets or are they formed around you? And if you have very low metallicity and can't form planets, if you have a planet, did you capture it? It's a fun idea.
Thank you for this talk. It was so interesting. I have 2 questions, but I'll just ask one for now. Your plot of occurrence rate as a function of age for sub-Neptunes.
Yeah.
Could you talk a little bit more about some of the potential effects of galactic evolution that you think could be causing this, like maybe increase or different shape?
Yeah, so I'll take away these points and we'll just go to these points. So when we were looking at this plot, and it was how do we have fewer planets around stars that are 5 to 9 billion years old than we do around young stars, one of the ideas, and I'm not a galactic evolution, I just play one on TV, when the galaxy was younger, star formation was more clustered and it was more highly irradiated and it was more concentrated essentially. And so planets that were born in those environments felt more dynamical history. These might get stripped away, a higher ionization rate. Maybe these planets didn't form in the first place to get stripped away. There's like a few different mechanisms that we just haven't modeled, I think is the point. And we know that they happen, we just don't know what their impact is on these planets. But we can't say that the stars that were born 3 to 9 gigayears ago are the same as the stars born today and would create the same planets. And I think that lack of control, that lack of control experiment is what makes this hard to interpret, right? We don't truly have a laboratory where we've got 5 billion years ago and today and be like, go.
Sorry, we're going to have to move on to the next talk.
Thank you.
So let's thank Jessie again for a wonderful review.